Yeah, so any questions about what we've done so far? Okay, last time we finished over here, we were talking about how the cross product of I and j is equal to k, and so on. So basically, the three vectors are at least, 1 second, it's possible I didn't get up to this part with this class. Does anyone remember exactly where we stopped in this class? Oh yeah. So did we do the right hand system?
I think we were about to get to it, but I don't think we got there yet.
Okay. So 1 second. Okay, yeah. Okay, so when, sorry, 1 second. Okay. So when we take the cross product of two vectors, like we said, so here, yeah, okay. If we have two vectors, v and w, and second, oh, once, yeah. Oh yeah. Okay, so if we have two vectors, v and w, then their cross product, we said, is going to be orthogonal to both v and w. So this is going to, let's say, be the cross product v cross w. Now, we can end up with two different vectors, either this one or this one. And it is useful to know which vector we end up with. And the way to do it is we look at the first vector and we can imagine a hand, and we put the fingers of our hand in the direction. So our fingers are going to be right over here. So here are our fingers. And then we extend, so then we put the palm of our hand in the direction of W. So here is where the palm of our hand is going to be. And we're talking about the right hand. And then we look at the direction in which our thumb is going to be going. So in this case, our thumb is going to be pointing in the upwards direction. If we put our fingers here and the palm of our hand here, and so we know that the vector v cross w is going to be pointing in the upwards direction. If, on the other hand, same situation, we have the vector v and the vector w. If we're looking at the vector w cross v, then now we put the fingers of our hand in the w direction because it comes first. So, and again, dealing with the right hand, our fingers go over here and the palm of our hand goes here. And now if you do this, you'd see that your thumb is going to be pointing in the downwards direction. And so this vector over here is going to be going down. So here's a picture of that. If we are looking at the vector v cross w, then we put the fingers of our hand in the v direction, the palm of our hand in the w direction, and then our thumb is sticking up, and that tells us the direction in which v cross w is going. Does that make sense?
It makes sense.
Okay, perfect. So here we have a couple geometric descriptions of the cross product. First, like we said, B cross W is orthogonal to both B and W. The second equation is fairly important, and it's very similar to the cosine equation that we saw with the dot product. So it says that the magnitude of V cross W is equal to the magnitude of V times the magnitude of W times sine of theta. And this should remind us somewhat of the dot product equation with cosine, which is that V dotted with W is equal to the magnitude of V times the magnitude of W times cosine of the angle between V and W. And as we can see, this over here is a constant, and so this is a constant, so they can be equal. To the above, this is a vector, and this over here is a constant. So we need to look at its magnitude, and that will tell us, and the magnitude of this is going to be equal to this constant. So in fact, the cross product to some degree plays the role of sine, and the dot product to some degree plays the role of cosine. And when I say that it plays the role of cosine or plays the role of sine, what I mean is we know that x is equal to r cosine theta when we're looking at polar coordinates, transformation between Cartesian polar coordinates, and y is equal to r sine of theta, where again we have a, well, let's say an R2, and this is our x, and this is our y, and we have a vector, and here's r, the length of this vector is r, then the x component over here is r cosine of theta, and the y component over here is r sine of theta. Now, when dealing with vectors themselves, we can use x to find our sine. And again, sine is the projection onto the y-axis over here. And so the cross product can be used to find y. It can be used to find the projection of our vector in the y direction, or the height of that vector. And the dot product, like we saw, can be used to find cosine. It can be used to find the projection in the x direction, which is why if we have two vectors, then the projection of u onto v is equal to u dotted with v over the magnitude of v. And that's because this is playing the role of cosine, like we saw in the proof. And so when we want to find the projection, which is kind of like finding the x coordinate, so here's u and here is v. If we want to find this projection over here, well, that's kind of like finding the x coordinate. And so we can use our dot product to do that. But if we wanted to find the height, we wanted to find this over here, then, well, we can use the fact that u is equal to the projection of u onto v plus the orthogonal component u onto v. And this over here is going to be that. But we can also use our sine over here, because that the sine is going to find us the height, our y. And we will see that this fact is going to be used quite a lot. So any question about these two equations? They're very important equations regarding cosine, regarding the cross product and the dot product. Any questions about them?
I had a question not about this, but I was just wondering, will the quiz be this Thursday or will it be posted up and we do it like on our own?
Sorry, will the quiz be what?
Will the quiz be this Thursday this week?
Oh, no, I'm gonna post the quiz on Friday, and you're gonna have like an hour to do it. So,
Oh, okay.
but
Will it
I
be
think
due
it'll
on?
be like you can start it at any time on Friday, and then you have an hour to finish it or something like that.
Okay, thank you.
Is there going to be like a schedule so we can like plan these things out, like as far as like the homework too, like in the quizzes, or are they just going to be like told to us the beginning of the week?
So I can, for the homeworks, I can put them more. I can schedule them. I can add the due dates for the homeworks a little earlier if that helps. The quizzes, there won't be a schedule, so I'll just let you know like a while before. But I'll try to put up the quiz for Friday so that you know, I guess when it's happening. I'll try to do that as quickly as possible. But yeah, the quizzes won't really have a schedule.
Okay, thank you.
Any other questions? No.
Yeah, I have a question about the projection of U onto the orthogonal vector of V. So, what is the final equation?
Hey, sorry for what? This over here?
Yep, yep.
Yeah,
Like
so
at
in
the
order
time.
so in order to find it, you can, like we saw, you can look at U. So the U projection onto V is going to be equal to U minus U. Oh, sorry, the orthogonal projection is U minus the projection of U onto V. And this we saw before, this equation. But regarding sine, like I said, it can also be used, and we will see how it's used in a couple of minutes, I guess.
Okay.
Yeah. Okay. Any other questions? Okay. So
I had another question real quick. On the syllabus, it says that there's going to be homework other than the online books that we have. Is there anything like that coming up soon?
So I don't do the homework. Like I don't post what homeworks you guys do. I just post the due date. And the homeworks that I'm given, I just put a due date for that. So whatever they give me, I'm just gonna put a due date and not really ask that many questions. So yeah. So far it's what it's been, like the learning curve. I thought that they were gonna have learning curve homeworks and regular homeworks, but they haven't been posting them. So
Okay.
oh, sorry about that. Okay. So let's look at the following examples. They want they want us to find the cross product of V and W over here using the geometric properties of the cross product. So I am going to skip this problem because it's not that relevant to multivariable. Generally, when we find cross products, you can just look at you can just do the cross product. So I'm not going to focus that much on this. An interesting equation that we get out of what we just talked about is that W cross V is equal to negative V cross W, and we can see why this is for two reasons. One of them is geometric, and one of them uses the equation that we just talked about. So the geometric interpretation is fairly easy. Again, if this is V and this is W, so V cross W is this vector, and then negative V, negative, this is negative V cross W, but it's also W cross V. And so we have that negative V cross W is equal to W cross V. And, okay, actually, I'm not going to, this is a good way of looking at it. Okay. So, yeah. So, like we said, W cross V is equal to negative V cross W. V cross V is equal to 0. The best way to see that is from the equation that the magnitude of V cross W is equal to the magnitude of V times the magnitude of W times sine of the angle between these two vectors. So if we have that the angle between, if we have V and V again, we're looking at V cross V, then the angle between them is 0. So V cross V, this is going to be equal to magnitude of V squared times sine of 0, which is equal to 0. And so the magnitude of V cross V is equal to 0. But if the magnitude of the vector is equal to 0, then that vector is equal to 0, so V cross V is equal to 0. Yeah, so V cross V is equal to 0. Similarly, you can use the same exact strategy to show that V cross W is equal to 0 if a W is equal to lambda V. And in order to show that this is an only if, well, so let's imagine that V does not equal to lambda W, then a V cross W, again, the magnitude of this is going to be equal to the magnitude of V times the magnitude of W times sine the angle between them. And now, because that neither of this is 0, this is not equal to 0. This is not going to be equal to 0. And if the angle between these two things is not 0, then this is not going to be equal to 0. As long as this angle is not 0 or pi. And so this, if this does not hold, then this is not 0, and so then this is not 0. But then that means that V cross W is not equal to the 0 vector. Any questions about this? Okay. We can move the scalar around. And okay. So another interesting thing about the cross product when looking at I, J, and K, because that the cross product always gives you the vector orthogonal to the two vectors. If we look at the vector, here's x, okay. Here's x, y, and z. And if we look at the vector I over here, j over here, and k over here, then ij cross j, that will give us this vector over here, so that equals k, and so on. So each one of these, when you take the cross product, gives you the other one. You have to look at the right-hand rule in order to make sure that you are going in the correct direction. But I cross j is equal to k, which tells us that j cross I is equal to negative k, and so on and so forth. So now they want us to use these relations to calculate what I plus k cross 3j plus 5k is. We probably won't see that many problems like this, I don't think, but just to make sure that we know what's going on, we can distribute So that's the first step. And then this over here, you have 2i cross 3j becomes 6i cross j. And then 2 times 5 and ik becomes 10ik, and so on and so forth. And then over here we get 6k, because that becomes k, minus 10j, that becomes j, and so on. And that's the resulting vector. So over here, they ask us a physics question, which I am going to skip right now. But it seems like what they're trying to find is the components in the y direction of some force, which is why they're using the cross product, which involves sign. But again, I'm not going to focus on this question just because that actually fine. Let's look at it quickly. So we're looking at 1 second. Okay, yeah, no, sorry. I'm not gonna put this question right now. This question, however, is dealing with torque, so it is to some degree a little bit more relevant, I think. So they have we're turning these two wrenches, and we have in one case we're applying force over here with R1 distance away, and in the other case we're applying the force like this with R2 distance away, and they want us to find the torque. And the torque is just defined to be R cross F. So it's this cross that over there. And interestingly, the torque will, because it's the cross product, it will be pointing out of, it will be orthogonal to both of these vectors, so kind of be pointing out of the page. And that's where the force of the torque will be going, out of the page, at least in this direction. So in this example, in the first case, they have the F1, the first force is equal to this vector, and R1 is equal to this vector. And in the second case, they have F1 is equal to this vector, and R2 is equal to that vector. So the first torque, T1, which again is going to be R1 cross F1, where this is R1, this is F1. Well, that's going to be equal, and because that we have the components over here are 0, 60, 0, F1 is really 60J. So this is going to, and R1 over here is going to be 0.5I. This is going to be 0.5I cross 60J, and this is going to be equal to 0.5 times 60 I cross J, which is going to be equal to 30 times K, because that's K. And this K actually, you can imagine a Z direction over here. It won't be the correct grid, because you generally would have X, Y, Z like this, but we can actually look at it this way here, X, Y, Z like this, and the wrench would be going in the X direction. So here's my wrench right over here, and the force being applied to the wrench is coming from the negative Y direction, so it's something like that. Here's my F1. And what we ended up seeing is that the torque is in the Z direction. It's in the K component. It has 30 K components, so it's in the Z direction. Any questions about this? Okay. And for the second one, we also have the second torque. Well, that's going to be R2 cross F2. Now R2 is going to be 0.3I, and then F cross, and then F2. So now F2 over here is 50I, and then sorry, minus 50J. And so this is going to be So this I over here, when it gets multiplied in here, the I's are going to cancel. And so then the next part is going to be the 0.3I cross minus 50. Okay. Right? Okay. And that, I guess, should give us, well, what's 0.3? Well, yeah, 0.3 times 50. Okay. So minus over here. Okay. Any questions about this? Yeah. So now, like I said, this equation can be used to find the height between, so if you have V over here, and if you have W, and you want to find this height over here, that height, so let's call this H, then we can use this equation to find that height. And the reason we would want to find this height is there are three shapes that they want us to know. Using the cross product, they want us to be able to find the area of those shapes. And there are only three, so it's important to memorize the three equations for those three shapes. The first one is if I take a vector V over here, and I take a vector W over here, so here's V and here's W, and I make a parallelogram out of them. So here's my parallelogram, like that. Then they would like us to be able to find the area of this parallelogram. And in order to find the area of this parallelogram, we need the base, which is going to be the magnitude of V, times the height, times this height over here. So that's this height from here to there. Now, the height is the projection of U, of W onto onto the y coordinate, because this over here is the y coordinate. So if my W over here was, let's imagine an R, like the magnitude of W times sine of theta, where theta is this angle over here, this is equal to y, right? Because that y is the projection, sine is the projection of this magnitude, it's like R, onto the y coordinate. So it's going to be equal to y, and this is going to be equal to my height. So the area of this parallelogram is going to be equal to the base, which is the magnitude of V, times this over here, which is the height, times height, which is the magnitude of W, times sine of theta. But this over here, we know, is this. So this is going to be equal to the magnitude of V cross W. So the area of this parallelogram is the magnitude of V cross W. So again, if you have two vectors and they create a parallelogram, you just continue to add V over here, you add W over here, and you want to know the area of this, it's going to be the magnitude of V cross W. So this is one important shape that they want us to know how to use the cross product to find the area for it. And then another shape is the triangle. So Again, if you have V and W, well, we can create a triangle out of them, like that. And they would like us to find the area of this triangle. Well, we can think about creating this parallelogram that we already created. And the area of this triangle is half the area of that parallelogram. So this is area 1 for this over here. And A2 is going to be the area of this triangle. So A2 is going to be equal 1/2 of the magnitude of V cross W. Any questions about this? Is it clear?
It's clear.
So, like I said, over here we have the first example of a parallelogram, and they tell us that the magnitude, the area of this parallelogram is going to be the magnitude of V cross W is equal to this over here. And now the area of this triangle is going to be 1/2 of that. Okay. So, in fact, we don't even have to remember that many equations for everything that we did. The projections, these areas. We honestly, and even a lot of the theorems that we looked at regarding the fact that the dot product of orthogonal vectors is 0, or the cross product of parallel vectors is 0. We honestly only need to remember these two equations. And a lot of these facts follow almost directly. So this again dealing with the projections, and this dealing with area. So the dot product deals with projections because it finds the x coordinate, which is basically the projection, and the cross product deals with areas because it finds the y coordinate, or the height, and the height helps us find areas. Okay. So now they want to add a third shape, and it's the parallelepiped. It's this over here. And those are the only three shapes that we need to know the area for using the cross product. There are going to be, actually, I don't think we're doing integration in this class. So these are really the only three shapes that we need to know the area for, at least using the cross product. The third one is if we have three vectors, V, so which ones? We have three vectors, V over here, W here, and U over here. So V, W, and U. Now the V and the W create a parallelogram like we saw. And we can use the U to create a parallelepiped, which is something like this. And this is going to be, we want to find the area of this thing, or sorry, the volume. So this is going to be A3. So now the volume of this thing is the base, which is this over here, times the height. And the height we're going to figure out in a second. But first, in order to find the green one, the base, well, that's pretty easy. The base is going to be equal to the area of the parallelogram over here, which, like we said, was the magnitude of V cross U. Now, the area of the whole thing is equal to the base times the height. And then this is going to be equal to V, the magnitude of V cross U. Now, how do we find the height? So, something interesting that we can do is we can look at the cross product of, oh, 1 second, oh, this is W, sorry about this. So, yeah, okay. Okay, this vector over here is W. So then this over here is V cross W. And then this over here is V cross W. Okay, so now we can look at the cross product of V and W. So that's this vector over here. And if you think about it, it is it's pointing directly out. Again, it's orthogonal to both V and to W. So it's pointing directly out. Well, let's imagine that we're sitting in a plane that V and W are in some big plane, pointing directly out of that. And so then the height of this parallelepiped is going to be the projection of this U onto V cross W. It's going to be, sorry, it's going to be this over here. Let's say the V cross W is this vector, slightly bigger. So then the height is going to be this over here, which is the projection of U onto this vector over here, the green vector, which is V cross W. So now when we look for a projection, we sorry. Yeah, so when we look at this projection, the projection is going to be U dotted with V cross W over the magnitude of V cross W. And this is going to be our height. So now the area is going to be this over here times U dotted with V cross W over the magnitude of V cross W. And now these two cancel. So it's going to be U dotted with V cross W. So going back here. And yeah, they take the absolute value just because the volumes are positive. But again, like we were talking about before, the volume of this parallelepiped is the area times the height, area of the base times the height. The area of the base is the magnitude of V cross W, and the height is U, the magnitude of U times cosine of theta, where theta is the angle between V cross W and U. Okay, but this over here, like we said, it's equal to the dot product. And so that tells us that the volume of this parallelepiped is U dotted with V cross W. So sorry, U dotted with V cross W. Any questions about this? Okay, so then the three areas that we need to remember. For A1, which was the area of the parallelepiped between two vectors, we said it was the magnitude of V cross W. For A2, which was the triangle between created by these two vectors, we said that this was 1/2 of V cross W. And for A3, which was the parallelepiped where we added a third dimension with another vector, this was equal to the magnitude of U dotted with V cross W. Okay.
I had a quick question.
Yeah.
Should if we were like given a shape, should we be able to like know how to like derive the formulas from the shape itself?
No, I would recommend that you know how to do it just because that it will help you memorize the equations, but no, you don't have to derive it.
Okay.
Professor, I think the last one you meant volume, right? Not area.
Sorry, yeah, area. Okay. Or, yeah. Okay, that's to be free, whatever. Thanks. Okay, so now, uh, so they call this the scalar triple product. Honestly, I've not really uh, seen it used that much, uh, other than for parallelepipeds. But an interesting thing about it, it's really the determinant of the vectors u, v, and w. So I'm not going to go through this proof in detail myself, but just to look at what they do. U dotted with v cross w, well, that will be u over here dotted with this, which is v cross w, and then this is u1, and then u2 and u3, you just dot them together. And then this is like putting a u1 over here, and then times this and then right, you get rid of this, and then you have this matrix over here, which is this matrix, or the determinant of that matrix, and then minus a u2, which is this over here, and then you get rid of these. And okay, at this point it's a mess, but that's, I think, understood. And then that's equal to the determinant of this matrix, which is the determinant of u, v, w. So just to clarify, this is equal to u1, sorry, the determinant u1, u2, u3, v1, v2, v3, and w1, w2, w3. Any questions about this? So something else that you can do if you have a parallelepiped is you can, instead of looking at this, you can look at the determinant of u1, u2, u3, dot, 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 and so on. So yeah, you put the v over here and the w over here. Okay. So that over here is what we have over here. The volume, which is the scalar product, which is this, scalar triple product, sorry, which is this, is equal to the determinant. Okay. So now they give us the following two vectors, v and w, and they want us to find the area of the parallelogram created by them. And then they want us to find the volume of the parallelepiped in figure 12, where now we are looking at 6 over here. So this over here in the z direction, right, we have v and w, and now my u over here, u is equal to 6k. Okay, so let's first do the first one. So for A, we know that the area, which is A1, whatever, is going to be equal to the magnitude of V cross W. Okay, so now the V cross W is going to be equal to IJK, and then we are going to have 1, 4, and 5, and -2, -1, and 2. So this is going to be equal to I times 8 minus, but then you have a minus over here, so it's going to be plus 5, minus j, and then we're going to have 2, and then minus minus again, so plus 10, and then plus a k, and then we're going to have -1, and then minus minus again, so plus 8. So this is going to be equal to the vector 13, and then this negative, so this is negative 12, and then this over here is 7. So this is going to be my vector, 13, negative 12, and 7. Now my area again. So this is going to be equal to 13, negative 12, and 7. So then the magnitude, oh, sorry, this is going to be equal to the magnitude of this, which is going to be equal to the square root 13 squared plus negative 12, negative 12 squared plus 7 squared. And that's going to be the area. And they tell us that that's approximately 19. And then for the second problem, now for the second problem, all we really need to do over here, because we know that the let's say V3 again. So this over here is going to be my U dotted with, or the absolute value of U dotted with V cross W, which is going to be equal to the magnitude of, okay, and then we're going to have 0, 0, and 6. That's going to be our U dotted with 13, negative 12, and 7, which is going to be equal to 6 times 7. So that's going to be that volume. So yeah, 6 times 7, 42. Okay, I think we're going to stop here for today. Do you have any questions? No questions?
Actually, I have a question.
Yeah.
Can you explain again on projection?
Explain like projection in general.
I mean,
How to get.
how it's related to orthogonal projection that you mentioned before, like.
Oh, okay, so fine. Orthogonal. Yeah. So if you have. Sorry. Okay, we're finishing. Okay, yeah, I think I have some time. So if you have V and you have W, then the projection down here is going to be equal to W dotted with V over the magnitude of V. And this is the projection of W onto V. Now, the orthogonal component, which is going to be this over here, well, we know by the tail rule of addition that W over here, so W is going to be equal to the red line, which is the projection of W onto V, plus the green line, which is going to be the orthogonal component. Right?
Mm-hmm.
Yeah. So now the orthogonal component is going to be equal to W minus the projection. Yeah?
Okay, I got it. Yeah.
Okay, perfect. Any other questions?
I'm good.
Okay, so I'll see you guys next time, and have a nice day.